Hello and welcome to General Chemistry 1. This is Professor Burns and I will be your instructor for the semester. I've made a series of voiceover PowerPoints to help you with your learning, and hopefully they will give you a little bit more instruction over reading the textbook. So here we go. Lecture 1-1, Chemistry, the Science of Change. As you all know, we generally do things by the scientific method, and the definition here is a path of discovery that leads from question and observation to a law or a hypothesis and then to theory, combined with experimental verification of the hypothesis, and any modifications are necessary of the theory. Laws are more akin to mathematical operations, like the law of gravity. Hypothesis is an estimated guess, an educated guess. However, that term is often confused with the layman's term of theory. In layman's term, a theory is actually a scientific hypothesis. I have a theory that happened that way is a usual sentence that you might hear when it's really not a theory. In science, a theory is a combination of many hypotheses, laws that make up a general set of rules, like the Big Bang Theory. So again, here to stress, a law is a statement that summarizes a vast number of experimental observations that can then describe or predict some aspect of the universe. A hypothesis is a tentative explanation for observations. For example, a hypothesis might be, there's a car going slow up here on the highway, about 45 miles an hour. It's probably an old person driving. That's a hypothesis. A theory is a well-substantiated, comprehensive, and testable explanation of a particular aspect of nature. Theories abound in chemistry, in physics, biology, mathematics, and other areas of science. Chemistry can be defined as the study of matter and the changes that matter undergoes. As a matter of fact, those changes involve the transfer of energy. Matter, when it changes, often changes in composition, properties, or some other observation that we can make. Matter is something that occupies space and has mass. And as I was told once by a student, well, if it occupies space, that's volume. If it has mass, mass divided by volume is density. So he simply stated that matter was anything that has density. I think I might agree with that kind of definition. Change. Definition is the process of becoming different. Change is one of those words that we often use circular definitions. Change is the process of changing. That's a circular definition. So we try to use something different. In this case, the process of becoming different. Well, let's quickly look at the states of matter. You should probably know these from previous exposures to science in high school. For a solid, the particles are packed closely together in a very orderly fashion, and those particles have very little freedom of motion. And finally, no matter where you put them, they do not conform to the shape of the container. Imagine putting a marble in a beaker. It's not going to change shape to fit the beaker. Next, liquids. Liquids are close together, but are not held rigidly in position. That means that they can flow. And some aspects of liquids are due to the nature that they can flow. Things like viscosity and surface tension. So the particles are free to move past each other. And when put in a container, they will conform to the shape that they fill within the container. And finally, let's look at gases. Gases, the particles are randomly spread apart. As a matter of fact, they're so far spread that when we talk about density of gases is generally 1,000 times or more less than that of liquids and solids. They have complete freedom of motion. They go where they want to go, and they conform to the shape and volume of the container that we put them in. Here are the typical changes of state. Going from solid to liquid is called melting. Going the other direction, from liquid to solid, is freezing. Most should be familiar with that. Going from liquid to vapor is called vaporization. Going from vapor back to liquid is called condensation. And there are two others. Some of you will be familiar with it, and some of you won't. And that is down here at the bottom. Going from a solid to a gas is called sublimation. The common substance that we look at for sublimation would be dry ice or CO2. CO2 comes in pellets or blocks, and they're solid, but because the room temperature is generally above carbon dioxide's sublimation point, which is minus 78 degrees Celsius, the carbon dioxide then leaves the solid as a gas. And the opposite process is deposition. A fun experiment that could be done with deposition is to take a beaker and put it on a hot plate or above a Bunsen burner and put some iodine in there. Iodine is a solid at room temperature. And then put up here on top a watch glass that has ice on it. And as this heats up, the iodine solid becomes iodine vapor. That is, it sublimes. And then when it gets up here to the ice is cool enough to cause deposition of the iodine crystals onto the cool surface. With these, there are particular points that we would talk about. If we hold our pressure steady and we draw a line across, you'll notice that this constant pressure line crosses two other lines. The first point is here, as we go from solid and we hit this line between solid and liquid, This is the melting point. What happens at the melting point is you have both solid and liquid together at that temperature. If this was water, that'd be 0 degrees Celsius. Over here, where the liquid comes in contact with the gas, that's the boiling point. At the boiling point, we have liquid and gas present together at the same time. Also, if this line was drawn lower and it only crossed this one line between solid and gas, that point there is called the sublimation point. That point is where we have a solid and a gas existing together at the same temperature. Don't worry about the triple point. We saved that discussion for 152, and the critical point also, we saved that for 152. So here's a table basically showing those typical changes of state. A solid, the upper temperature of the solid can either be a melting point or a sublimation point. Liquids have an upper and a lower point. Their lower temperature is a melting point, and their upper temperature is a boiling point. And then finally, gases generally only have a lower point, which can either be a boiling point or a sublimation point. Next topic, atoms and molecules. Here's another couple of definitions. An atom is the smallest particle of an element that can enter into a chemical combination. It's the smallest particle of an element. We will find later that some elements are composed of multiple atoms. For example, hydrogen is 2 hydrogen atoms connected together. A molecule is a substance composed of 2 or more atoms, which may or may not necessarily be different. So, for example, H2 is a molecule of hydrogen. H2O is a molecule of water. Looking at this from a dichotomous point of view, matter can be divided up into pure substances and mixtures. Basically, to get mixtures, we take pure substances and combine them together in a physical manner. The pure substances are going to be elements, that is the individual elements on the periodic table, the 118 that we currently have, and then compounds, those things that are made up of elements. So the work between elements and compounds tends to be chemical. For mixtures, there are 2 types, homogeneous and heterogeneous. And homogeneous compounds tend to be distributed evenly throughout. It's hard to tell different parts or different compositions from one place to another, like air. Whereas heterogeneous mixtures, you can definitely tell there are different parts in it. Concrete, for example. There are rocks and the binding material and little rocks and big rocks and so forth. So let's look at the definitions. Pure substances, a form of matter that has a definite composition and distinct properties. An element is a substance that cannot be separated into simpler substances by chemical means. And finally, a compound is a substance composed of two or more elements. Two or more elements is very important here. Makes a compound a slightly different thing from a molecule. A molecule was two or more atoms, and they could be of the same element. But compounds, you have to have two or more elements present. So we can actually look at elements, compounds, and molecules using a Venn diagram. Elements, that is the left oval here, kind of a pinkish color, come in two forms. They come in monatomic, that is elements involving only one atom, things like sodium, potassium, almost all the metals, things like germanium, zinc. Then there's a few that are molecules. So this area here, these are elements in this oval. And over here in the blue oval, these are molecules. Well, I lost my ability to spell there. Molecules. What happens here in this area, it's kind of purplish there in the middle, are elements that are molecules. And there's a number of them, like hydrogen that I exposed you to before. Various forms of carbon come in molecules like diamond, graphite. Sulfur comes in an octamer, so it has 8 units to it. The rest of the molecules in the blue area are compounds because they have one or more. They have two or more, excuse me. My bad there. 2 or more elements in them. So again, just to reiterate, monatomic elements over here in this red area here. Polyatomic or molecular elements in this purplish area, and compounds in the blue area. Well, thus far we have 118 elements. The first 94 elements can be found somewhere naturally on the Earth. 80 of the first 82, that is ending at lead, have stable isotopes. There are 2 that do not. Technetium, element 43, has no stable isotopes. All are radioactive. And promethium is the same, has no stable isotopes. In addition, there are a number of elements that have been created by scientists. Most of the radioactive ones and the higher or the heavy metals Some of them were created first, and then we were able to find them on the Earth, like technetium. We've been able to find that in trace amounts on the Earth. But most of the technetium that we use is produced artificially. So here are the list of the diatomic elements, and I've also colored those in. It says 7, there are actually 8 listed here, and I have not fixed this slide, so this is actually 8. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine are the 8 diatomic, with hydrogen, nitrogen, oxygen, fluorine, and chlorine. These are all gases. Bromine is a liquid, and iodine and astatine are solids. And astatine is highly radioactive. The polyatomic elements include phosphorus. P4 is called white phosphorus. Sulfur and selenium come as octamers, very similar to each other in structure. Compounds, again, they're composed of 2 or more elements that are chemically united in fixed proportions. H2O. As a result, each different compound has a distinctive set of properties. These can be separated into simpler substances by chemical means. They can be separated into other compounds by decomposition, or they can be separated into individual elements, depending on what type of chemistry you're dealing with. Mixtures, again, they are a physical combination of 2 or more substances. The substances retain their distinct identities, and many times we can take a mixture apart and get the individual parts separated from each other. There tends to be no universal constant composition that occurs. Think about the different types or ways you can have a coffee. There is no one set way to have your coffee. And these can be separated by physical means. Again, to reiterate, homogeneous mixtures, the composition is the same throughout. Sodas, milk, and solder. Solder is the stuff that joins 2 pieces of metal together in a weld. That's what solder is. Heterogeneous mixtures, well, as you can see down here at the bottom, I could separate those out into individual nuts and candies. And over here on the right-hand side, we have sulfur sitting on a piece of rock. These are both heterogeneous mixtures. Physical properties. These are characteristics of matter that is not associated with any change in the chemical composition. Something that is red is red is red is red. It may be a little bit lighter red or a little bit darker red, but when we measure it by spectrophotometry, what we find is that the pattern of absorption of light is always the same. These can be observed and measured without changing the substance. Things like color, as I just mentioned, the melting point, and that's a melting point apparatus down here, or the fact that it's a gas, the state that it's in. Gases, liquids, solids are physical properties. Physical changes. Here we're going to change the state or property of the matter, but we're not going to change its chemical composition. During the process of change, the identity of the substance stays the same. When ice melts, you still have water. When you boil an egg, you still have an egg. As a matter of fact, somebody's figured out how to turn it back into the jelly type substance. Here, we're taking a road and just chopping it up. The rocks, the asphalt, all that is still the same. Chemical properties. This is behavior that is related to change in matter. That is, we're going to take the substance and make it into something else. These are determined by the chemical changes that are possible to be observed, not that are actually being observed. Things like flammability. That's a possible observation. Paper is flammable. Rocks tend not to be flammable. The alkali metals are high in reactivity. Throw sodium in a big chunk of sodium in a lake and you get an explosion. Whereas if you throw gold in a lake, not much is going to happen. There's not very much reactivity with gold. So those are chemical properties. Chemical change, on the other hand, is when it actually does something related to a property. When you burn a substance, when you digest a substance, when iron rusts, these are changes. They tend to be more of an action word, a verb. And the final two properties are extensive properties and intensive properties. Extensive properties depend upon how much stuff you have. Things like mass, volume, length, energy are example of extensive properties because you can add them together and you get something bigger. An example I like to use is energy when it comes to your car. If you have a 20-gallon tank, then you can go, let's say, 400 miles on that 20 gallons. But if you only had 10 gallons, you're only going to go 200 miles. But you'll say, but you get the same miles per gallon in each of those examples. That is true. That's why we have intensive properties. These are properties independent of the amount of matter present. So going 400 miles on 20 gallons is 20 miles per gallon. And going 200 miles on 10 gallons is also 20 miles per gallon. So oftentimes what we'll see with an intensive property is it will have 2 units in its measurement. Like density is grams per milliliter. 2 units associated with it. Some that don't are related to temperature, boiling points, melting points, sublimation points, specific heat has the units of joules per gram and degree Celsius. It has a multiple set of units so that we can see from the units the possibility of an intensive property.